Well, we're back. It's 10:45 Eastern Time. So the last activity of today workshop is day number 2, is the hands-on session BGP2. Ali will continue describing some scenarios. Specifically, I believe he will describe BGP hijacking with a simple example. What BGP hijacking is, and some activities or some techniques that are cited by the manners document, how to mitigate that. And then it will show an example. One of those ways is using, I believe, an access control. Ali, would you like to start the hands-on session BGP2?
Yeah, sure. Okay, so previously, like we've touched on a couple of BGP labs, such as like the basic configuration, how to configure attributes, local preference, and the MED. And there are like other also applications of, that are also covered in the lab. Now we're gonna present some security applications and attack that occurs across the internet. And also we're gonna present the mitigation techniques to counter these attacks. So the last two labs are basically some attacks, which the first one is like the IP spoofing and mitigation techniques, and lab 13 is performing BGP hijacking as well as how to counter this attack. So the organization of the labs is also similar as the one as the previous labs. We have the overview that talks about I just share my full screen. Yeah, we have the overview, like what are the definition of the attack, how can we mitigate it, what are the possible solutions that the network providers use, and so on. And we have like step-by-step directions on how to perform the attack and how to mitigate it. So BGP hijacking. Typically, when an attacker maliciously reroute internet traffic by advertising IP prefixes that are owned by other networks. So, and this also, okay. So this also occurs when an unauthorized network originates IP prefix. For example, as we see here, we have this scenario. There's a hijacking router, and basically what happens here is that the hijacking router advertises prefixes that are owned by the legitimate router. So let's say that a legitimate router, let's pretend that it owns the network 192.168.4.10. What's going to happen is that the hijacker is going to advertise this network. And as we mentioned before, because BGP selects the route that are having the less number of hops, on the router R2 is going when it like route traffic to the legitimate router, it will take this path, which is basically R1 and R2, because it's basically this is the route that has less number of hops. So this is a typical BGP hijacking scenario based on the like less number of hops. So why are we covering BGP hijacking attacks? Like although the BGP hijacking is an old problem, however, it still persists in our days. And as we can see here, like in April 2020, like there were over 8,000 prefixes that were rerouted from well-known networks. So now, how do we mitigate BGP attacks? So, in order to mitigate the attacks, one possible solution is to use IP prefix filters. These can limit the numbers of BGP route advertisement by configuring IP prefix filters. So, for example, let's say that the customer here owns the network 192.168.10/24, and what is going to happen is that the internet service provider is going to configure IP prefix filters to limit route advertisement, so that when the customer tries to advertise a network which is different than the one owned by the customer, let's say 192.168.2.0, the internet service provider is going to reject this route advertisement, and it's not going to propagate it for external networks. So the topology of flap 13 depicts the following scenario. Here we have campus 1, which is going to be the hijacker, and we have campus 2, which is going to be the victim. And basically what's going to happen is that router R1 is going to advertise routes that are owned by campus 2, so that when the internet service provider, and specifically router R3, needs to route the traffic to campus 2, it's going to select the shortest path, which is 192.168.13.0, instead of following the legitimate path, which is via R4, R2. So after R1 hijacked the BGP, the IP prefixes that are owned by the campus, what is going to happen, as we said, is that all the network traffic that's going to that has the destination campus 2 and passing through router R3 are going to be rerouted to the hijacker. And in order to mitigate the hijacking attack, this is basically gonna happen on the level of the internet service provider, where router R3 or similarly router R4 is going to configure IP prefix filters, so that when the router R1 tries to advertise any network or any prefix that's other than 192.168.1.0, this will not be accepted by router R3. And similarly, the same scenario occurs on router R4, that it's going to configure IP prefix filters to limit the route advertisement of campus 2. So the configuration of flap 13. First, let's begin with a hijacking scenario. So how do we hijack an IP prefix? Similarly, as we've seen before, we used to advertise networks so that they are learned by other external networks. And the same thing is applied. It's straightforward. As we've advertised other networks like 192.168.1.0, now we're gonna advertise or hijack the network 192.168.2.0. So now after this network is hijacked, the one which belongs to campus 2, the BGP neighbors such as router R3 and router R4 are going to insert another entry, another next hop to reach this destination. So let's say that we've already advertised the network that belongs to campus 2, that we hijacked it. If we see the configuration, the BGP table of router R3, as we see here, the network 192.168.2.0, it has the next hop 13.1, and 13.1 is basically the link between R1 and R3. And here, and this is the preferred path, as we said before, because it has the arrow sign. And in case this path is not valid, it's going to use the secondary or the legitimate path 34.2. So now the BGP, basically the hijacking scenario is like successful because router R3 was strict to use a different path for the legitimate network. And how can we validate the BGP hijacking scenario? Okay, so let's say that the traffic are have the destination campus 2 and they're passing through R3. If the BGP hijacking scenario works, it should be rerouted to router R1. In order to verify that, we can use the TCP dump command line. TCP dump. This basically captures the network traffic on. We specify the interface R1 ETH1, which basically face router R3, and this is the interface that we're interested in because this is where the hijacking. This is where the traffic is going to be routed to. And now let's try to ping. Let's try to like simulate a network flow that's going to campus 2, the victim, and let's start like they're passing through router R3. So in order to do that, we simply open the command line terminal of router R3 and try to ping campus 2 or the victim. And basically here the destination is not reachable because there's no reply back. But however, like our aim is to show that the BGP hijack the network is gonna be rerouted to campus 1, and this can be seen here. This is the TCP dump output of router R1. As we see here, we have packets that are sent from 13.2 and going to 2.0 to 2.1. And although like router R1 doesn't have this network, but it was able to successfully hijack and reroute the traffics. So now after the BGP hijacking scenario was successful, and we've seen that how the network traffic was rerouted into like to the attacker or the hijacker, how do we mitigate this hijacking scenario? And basically, this is done at the level of the internet service provider, where IP prefixes will be configured. So for example, router R3 is connected directly to campus 1 or customer or whatever. Uh, Router R3 is going to deploy or configure IP prefix filters to limit the network or the advertisement, and the same for router R4. So the IP prefix is done using this command. It's called IP prefix list, and the name of the prefix list that you want. The sequence number is 10. Here it's not really relevant. The sequence number has to be configured, and we permit only the network 192.168.1.0 that belongs to campus 1. Any other network that like any other network that's advertised and it doesn't match this network, it will be immediately dropped because there are no other rule other than this prefix list that's configured. And basically after configuring or assigning the prefix list, we have to assign it to the neighbor, and router R3 is responsible for campus 1. So the neighbor is 13.1, which is router R1, and the prefix list, the name of the prefix list, campus 1, and this is applied for inbound network traffic because basically router R3, why do we need the inbound network traffic? Because the hijacking is going to be like the advertisement is going to pass from router R1 into router R3. So after we configure the prefix list, now we can see that, okay, so the routing table of R3 should get back to normal. The campus 1 should advertise its network and campus 2 should advertise its network. And the BGP table of router R3 is as follows. Network 192.168.1.0, it's the normal path, 13.1, and the previously hijacked network 192.168.2.0 now has the next hop 34.2. So even though router R1 is still advertising the network of campus 2, router R3, after configuring the prefix list, is not going to accept this advertisement after this. And this could be, this is shown here. So now let's get back, let's go to the hands-on session as we will. Okay, so this is the BGP hijacking, and as we did before, okay, so the content here I'm gonna show the topology just right quick. Previously, what we did is that we've already covered all this content from assigning the IP addresses automatically. We've also covered other configuration such as section 2 and 3, which is configuring BGP on routers, because our aim in this lab is to show how do we perform BGP hijacking as well as how to mitigate it, and that's why we skipped all this process, but these are well documented step by step on each router. And we're now here in section 4, how to perform BGP hijacking. So first, let's validate the routing table of router R3 and make sure that the next hop for the campus 2.0 is the legitimate one, which is 34.2. We enter the VTYSH session and we show IP BGP. And here, as we can see, network 2, which belongs to campus 2, has the next hop 34.2, which is the legitimate route. Now, we want to hijack the campus 2. So this can be really done here by advertising the network 192.168.2.0. Let's enter to the terminal of router R1. Let's enter the VTYSH session to start configuring the terminal. And as we did before, we want to advertise the network 192.168. This is network 1. And the network that's going to be advertised is 192.168.2.0//24. To validate that now the BGP hijacking works, we go to router R3 terminal, VTYSH session. Again, we see that now the next hop is different and it's going to be routed to the hijacker, router R1. So let's move to let's validate this attack on router R1, and we want the TCP dump in order to capture the traffic. 1, 2, okay, and this interface R1 ETH1 is basically the one facing router R3. And let's try to ping campus 2 from router R3. Basically, as we see here, we have, I'm gonna stop now and check. Okay, so here, as we see, we have the traffic was routed to router R1, and the destination is 2.10. So now the BGP hijacking scenario works. Let's try to mitigate this scenario and using the BGP IP prefix filters. We're gonna go back to router R3 because this is basically the internet service provider in our example. Now, I'm going back to the content just to follow. And now the section is to how to mitigate BGP hijacking. And basically, I'm going to create an IP prefix list, and immediately I'm going to assign it to the neighbor, which is router R1. So first, create a prefix list, and basically what you can do is that just click on the tab and it will automatically fill it. And the name of the prefix list is campus1 and sequence number. and we're gonna permit the network 192.168.1.0. And one thing is that here we've listed this network and we didn't list any other network. And by default, IP prefix works that like the access list is that it matches on the first entry. If there's no match found, it will immediately drop the packet. So no need to cover other IP prefixes because these will not match this prefix. Now router BGP 100. Oh, I'm sorry, router BGP this 200, and basically we're gonna assign the prefix list to the neighbor 192.168.13.1. The name of the prefix list. The name of it is campus1, and it's applied for the inbound network traffic. So everything that comes from router R1 is going to be filtered using this prefix list. Okay. Now presumably like router 3 should filter all the network traffic from router R1, and what's going to happen is that router if we see the BGP table of router R3 previously, this network 192.168.2.0 had two next stops because basically it was advertised by two routers, R1 and R2, the hijacker and the victim. Now, after applying the prefix list, simply the only next hop that's going to be used is 192.168.34.2. And let's validate this again. On router R1, we're gonna also capture the network traffic, and we're gonna ping. That's exactly what we did. 168.2.10. This is campus 2, host 2. And on the captured network traffic on router R1, now we shouldn't receive anything because the traffic will not be routed to router R1. As we see here, no, this is only just like internal output, but basically we don't see any packet that has the destination 192.168.2.0, and this is basically how to mitigate BGP hijacking technique. And now also we can continue this work, and because basically we've mentioned that campus 1 the hijacker and campus 2 is the victim, but also campus 2 could be the hijacker. So simply on router R4 terminal, follow the same step to apply route filters. UISH session, the configure terminal. I'm pressing here the tab button so that it fills it automatically. And another IP prefix list, but here now on router R4 and campus 2. I'm gonna call it campus 2 because it corresponds to campus 2. Sequence number, and we're gonna permit only the network 192.168.4.0/24. Oh, .10. Mistake. And then router BGP 200, we'll assign it to the 192.168.24.1. This is basically the IP address of router R2, and the prefix list is called campus2, and we're going to apply it to campus network. And this is basically how we apply route filters on how do we perform BGP hijacking in addition to applying route filters in order to mitigate this attack. So that's it for Lab 13, which is basically BGP hijacking. We've covered how do we do the attack as well as how do we mitigate it. all the steps are covered in the manual, step by step. It's straightforward. And in addition, in the introduction section, there are other mitigation techniques. Here I jump to the introduction section. There are other mitigation techniques that are used, like, for example, the RPKI, this is just explaining, as well as the IP prefix filters here. So feel free to check it, and if there's any question. So this is another attack, the IP spoofing attack. So what is IP spoofing? The IP spoofing is basically when the attacker or malicious, like it originate packets with the source address other than those assigned to the origin host. So, and basically IP spoofing can be exploited in several ways, but mainly it's exploited to launch denial of service attacks. So let's see the scenario. We have the attacker here and we have the victim. So basically what's going to happen is that the attacker will spoof the IP address of host C, and it will originate packets having the source of the victim, and the destination is basically can be any host, for example host B. So host B, when it receives the packet, the spoofed packet, it will reply back to the source, and basically the source here is spoofed, so it will reply back to host HC. This is just a simple scenario where we show like one host B as the middle or the like amplifier, but basically if host A is pinging to like thousands of hosts or amplifier, all these hosts are going to ping back to host C, which and this is how the denial of service is executed. So IP spoofing, anti-spoofing techniques. There are like a couple of methods that you are used for to mitigate IP spoofing techniques, and route filtering is one of them. It's like a method to like select or identify the routes that are advertised from neighbor routers. So using IP prefix filters, we can like manipulate the traffic. We can specify which traffic we want to accept into our network based on several like attributes. For example, we can check on based on the source address. We can check on the destination, on the port, and other stuff. Uh, so this is a scenario where let's assume that router R2 is the internet service provider and it's connected to two customers. When customer 1 tries to spoof the IP address of customer 2, what's going to happen is router R2 is configured with IP prefix list so that it doesn't accept the spoof packet. Because basically, the internet service provider knows the network or that should be originated from customer 1. And as it sees that router R2 sees that packets have the source of customer 2 coming from this port. So immediately the prefix list, this packet will be dropped at this port. So the topology of the lab. Okay. So here we show a simple topology where we can where we can spoof the IP address of another host or another campus, whatever, and we show the role of the internet service provider in establishing or configuring IP prefix list to mitigate the IP spoofing attacks. And in our case here, we have campus 1. Campus 1 is basically going to be the spoofer, IP spoofer, and the victim is going to be campus 2. So overall, what's going to happen is that campus 1 is going to uh, uh, launch packets having the source 192.168.2.10 or so on. In order to provide that's what. In order to mitigate the IP spoofing, On router R2, will apply the appropriate route filters on campus 1 or its customer, and similarly, the same thing will be applied here on the other end, which is basically uh, router R3. So jumping to the configuration of the lab manual. First, our aim is to spoof the IP packets. So as we mentioned, we want to send packets that have different IP address from those assigned to the campus one in our case. So in order to do that, first host H1, we will assign an interface with the IP address of host H4. So in our case, we selected the loopback interface, and we assigned the IP address 192.168.4.10. And basically, this address belongs to host 4, as we mentioned. Okay, and then when we configure the interface with the spoofed IP packet, we can uh, try to ping two different hosts, which are H2 and H3. Basically, these two are the middle host, or like the amplifiers. And when these two hosts receive the spoofed packets from host H1, they're going to reply back to the source, which is basically 410. So in order to simultaneously ping two hosts at the same time from in one command, this fping is a program that allows to do that. We can specify, because basically host H1 now has multiple interfaces. It has like the loopback interface, which is contains the spoofed IP address, as well as it contains the direct link connected to R1. Basically, we don't want to send packets using the legitimate interface, or the one connected to router R1. Instead, we want to use the source 192.168.4.10, and our destination is going to be 2.10 as well as 3.10, which belong to host H1, H3. So in order to verify that after we ping these two hosts, H3 and H4, in order to verify the successful, let's say, denial of service attack here, we launched the TCP dump command in order to capture the traffic. And as we see here, that we have IP packets coming from host H3, represented by 192.168.3.10, coming to the host itself, host H4. And we have another also packets coming from 192.168.2.10 to this destination. And although host H4 didn't ping any of these two hosts, but they're replying back to the spoofed IP address. And this is how basically denial of service attacks. Um, and like those attacks basically on a wider scale, where we have like thousands of hosts that are act as amplifiers to target the victim. So after we've seen how the denial of service attacks works, and where we were able to successfully launch it from campus 1, what has to be done now is that the internet service provider, which is like responsible for somehow configuring or monitoring the network of its of the campus 1 and campus 2, should apply the necessary route filters, so that, for example, let's say here router R2 is directly connected to campus 1, and the internet service provider is basically knows that campus 1 only can only advertise IP packets that have the source 192.168.1.0. So any other packet that comes through this interface R2 ETH1 having a different or unmatched IP address, it's going to be dropped immediately. And similarly, this applies for router R3 that monitors campus 2 and checks if the packets that comes into that are like steered to other networks, external networks, also have the proper source IP address. So in order to, so now our aim is to basically filter based on the source IP address, because um, this is the kind of the root of the DDoS attack, is that the source IP address is spoofed. So in order to monitor at the level of the source IP address, we use the IP tables utility, and this is basically implemented in Linux. This is above FRR. We didn't use FRR here. And what IP tables does is that it provides filtering capabilities to the Linux host or router or whatever, and based on several attributes. For example, we can filter based on the source, we can filter based on the interface, port, TCP, and other stuff. And in our case here, we write the command IP tables in order to insert an entry into the routing table of router R2. The -A forward specifies that this entry is for inbound network traffic that are not local, because basically the internet we wanna the internet service provider is like is considered as a transit where packets are uh, traversed from campus 1 to campus 2. So the attack is going to occur at the level of the campus, and that's why we like kind of specify -A forward. It's for like not the packets that are not local. And here we specify the address. This is -S is the source IP address. This 192.168.1.0 that belongs to campus 2. And also we have to specify the interface, because basically the traffic that comes from campus 1 belongs to the interface R2HH1. And in case a packet having only this source matches only this source IP address and coming from this network, we accept it. Or any other packet that does not have this source address will be immediately rejected if it comes if it's like comes through the interface R2ETH1. And this can be done using another command, which is basically insert another entry in the IP tables. Basically here we specify the 0/0 is basically all possible IP addresses that comes from this interface will be dropped. So briefly, what's happening here is that any packet that comes through this interface, R2ETH1, will go through these two entries. If it matches this source address, it will be accepted. Otherwise, it will be dropped. This is like a sequential matching mechanism. And now, if we try to ping from host H1 to host H3, host H4, H2 and H3 using the source address of host H4, what's going to happen is that because basically the internet service provider applied the appropriate load filters, this host H4 will not receive any packet because they are immediately dropped at the level of the internet service provider. And now moving to the hands-on session. We've also created and pre-configured all the steps before the IP spoofing, but they're well documented in the lab manual here in the content tab. And this is basically the topology. And as we see here in the manual, everything is well documented. We've already configured everything from BGP neighborhood establishment to like this section. Configuring BGP routers is already covered in this lab. Also, networks are advertised, and we immediately we're gonna immediately jump to the section which is performing IP spoofing. So this is our topology. The BGP neighborhood is established, networks are advertised, and everything is working in a perfectly normal case scenario. What's going to happen here is that first we enter the terminal of H1, and as we said before in the content tab here, the first thing we want to do is that we have to spoof the IP packet of the host H4 which is present in campus 2. So in order to do that, we will configure the loopback interface. First, VTY ifconfig, the ifconfig loopback interface 192.168.4.10. Now we can validate that, and if we see here, the loopback interface have the network 192.168.4.10. So perfect. Now host H1 is ready to launch spoof IP packets and perform DDoS attacks on host H4. Let's verify that. We enter to the terminal of host H4, and as we did before, we're gonna capture the traffic. TCP dump -I corresponds to the interface of this interface facing R3, which is or we can verify that. Okay, for ETH 0. This is the interface facing router H4. And now what we're gonna do is that we will launch the fping command. And by the way, fping is not installed by default on Linux. We installed it, but in the post it's already installed. So okay, so now we can specify the source, which is 192.168.4.10, and we have to specify our destination. The first destination is going to be 192.168.2.10, which corresponds to host H2, and the second one is 192.168.3.10. As we can see here, the traffic, or the, as we might say, the DDoS attack is being held on host H4, where we see two hosts trying to ping host H4, 2.10 and 3.10. And host H1 can amplify, as we mentioned before, can amplify this attack by pinging thousands of hosts, as well as increasing the payload of the packet. Now we've seen how do we spoof the IP source address. Let's move to how to mitigate it. The R2 router R2 is the router inside the internet service provider. We launched the terminal of router R2, and here I'm going back to the content. As we see here, we've covered the denial of service attack on host H4, and now we will move to the mitigation section, sorry. And here so the first entry in the IP tables, as we mentioned before, forward, and the source is going to be 192.168.1.0. So every packet that matches this network is going, it's coming from the interface. -I is the interface. ETH1 J accept. We can accept this. Another entry is going to deal with the spoofed packets, which does not match this forward -s and all other packet IP addresses are to the same interface, because basically we're dealing with campus one, and we accept this. Oh, I'm sorry, we drop it because this is basically the spoofed IP packet. I missed IP tables. That was a typo. Okay. So now we've configured two entries in the IP table of router R2. Now, if we try to ping host H2 and H3 using the spoofed IP packet of H1 to perform the DDoS attack, H4 should not receive any packet. And let's validate that. This is host H4 ping /src 192.168.4.10. This is the spoof. 168.2.10, 192.168.3.10, and we move back to the this is the terminal of host H4, also H4 ETH0, and here we're trying to ping these two hosts, but host H4 didn't receive any packet, which basically verifies that we were able to mitigate the IP spoofing attack that was launched by host H1 on host H4 using the two amplifiers, host H2 and host H4. And similarly, as we configured entries in the IP table of router R2, we can similarly do the same thing on router R3, where we manage campus 2, so that we filter the IP addresses that are coming from router R4. So that's basically about IP. We've covered how do we perform the spoofing and how can the IP spoofing be used to launch like a simple or denial of service attack using two hosts, H2 and H3. The victim is host H4. And also we've covered how do we mitigate IP spoofing or DDoS by applying the appropriate load filters on the level of the internet service provider, because basically in real life scenario, as mentioned earlier, that no entity should be trusted, and IP prefix filters or any other technique that's recommended must be used in order to prevent against attacks such as, for example, BGP hijacking, IP spoofing, denial of service attack, and so on. That's really about the two basic two attacks that were covered, the BGP hijacking and the DDoS attacks. Feel free to ask any question regarding anything you want, setting the lab manual, attack, or whatever.
Thank you, Ali. I just have a few comments, because we're dealing here with a virtual router, and a real router might have access control lists implemented in the data plane. Do you have that capability when building these labs using equivalent of ACLs in virtual interfaces?
Basically, what we did is that we used the IP tables because we wanted to filter based on the source IP address, And in FRR, we weren't able to do that. Basically, the DDoS attack or the IP spoofing uh, deals with the IP address, and this couldn't be done with the supported access list that covered by FRR routing. But
But
there are other vendors that support the
well,
access list based on the source IP address.
so this is one limitation that you found when working with this virtual router FR routing, but it is because we're working with a virtual router. But if we had
Exactly.
in a real hardware, we would use an access control list.
Yes, exactly, and that's pretty like could be easily found in multiple vendors. In their manual page, they show that their access list can be based on the destination, source, and other stuff. But specifically in this, and because we're like emulating using Mininet and specifically FRR to configure the routers, we weren't able to filter based on the like and with the capability supported to FRR, and that's why we used uh, the utility IP tables that is already like installed in the kernel, in Linux kernel.
When you use FR routing in programmable switches, the edge core switch, which is a programmable switch, and you can write a program. Do you have that capability in the lab? Did you try that?
And the programmable switch?
Yes.
Um,
So you have the capability to use FR routing in with programmable switches, and it works, and BGP
yes,
works.
yes, exactly, yeah.
Now, can you write your own program in P4 and write your access control list? Did you try that? Try to emulate this attack in the real hardware?
Oh, no, I didn't. But I think like because basically we try to install FRR on the programmable switch, the same limitation is going to be applied on the like regarding the configuration or the capabilities of FRR, because basically this here we're emulating the same environment. So there's nothing that's like there's no additional configuration or features that are supported to the vendor and not supported here in our environment. So I think it should be done at the level of the P4 program where we like configure like table entries to apply access list instead of using FRR configuration.
Thank you. There is an observation here. Justin, prefix lists are more common when doing routing filtering with the BGP. Also, autonomous system path lists are common. That's an observation. So we will wait for if there is any question. So there was a comment before or a question if the virtual machine that is used for these BGP labs will be available. Yes, we will put a link in our website, in the workshop website, and with the link to download these virtual machines. Now, for the BGP labs and the network tools and protocol labs, the one that we used yesterday, is straightforward. Anybody could just download the virtual machine and the labs will be contained there. However, there are more complex labs. The Persona labs, those require 7 virtual machines and interconnection of several networks, so that is more complex. But at least for BGP and network tools and protocols, the virtual machine will be available. One comment about using download a virtual machine, the one that we use for the network tools and protocol, is that some of the labs are really CPU intensive, so you might not have the performance that we had when run on the cloud. But other than that, it should work. So that will be available. Okay, there is no No questions, not other comments. Thank you, Ali, very much.
Thank you, Jorge.
I will display my screen now.